the ice is moving faster than it should. Not faster than last year, faster than any model predicted, faster than any model thought was possible. In 2023, a research team drilled into a glacier that wasn't supposed to be melting yet. They pulled up cores of ancient ice, frozen records of the past 800,000 years, and buried inside those cores was something that rewrote what we thought we knew about how this planet ends. Not the ending humanity imagined, a faster one. This is the story of what scientists found at the bottom of the world, and why the math they trusted for decades may have been wrong. Antarctica is not just cold, it is ancient cold. The ice sheet sitting on that continent is 2 miles thick in places. 2 miles. That's the height of 3 Empire State Buildings stacked on top of each other. And then you add 3 more on top of that. That ice took hundreds of thousands of years to build. It holds secrets. Inside those frozen layers are trapped air bubbles from prehistoric atmospheres, dust from volcanic eruptions that happened before humans existed, chemical signatures of ancient temperatures. Scientists have been reading those layers like pages in a history book, and for decades, that book told a consistent story. The story went like this: ice sheets are slow. They respond to warming over centuries. Even if we push the climate hard, Antarctica would hold for a very long time. Its collapse, if it came, would be a slow-motion disaster, a problem from many generations from now. That story made sense. The math supported it. The models agreed. And then the math stopped working. In February 2023, Antarctic sea ice hit a record low. Not a small record, not a "this is slightly worse than before" kind of record. The sea ice extent was nearly 1 million square kilometers below the previous record low. To put that in terms you can actually picture, that's an area larger than the state of Texas, of ice that was supposed to be there, simply gone. Researchers at first assumed this was a statistical anomaly, a bad year. Climate is variable. One bad year doesn't mean a trend. Then 2024 came, and the numbers were worse. Scientists at the British Antarctic Survey began cross-referencing satellite data with what they were finding on the ground, and what they found created what one researcher described, in a rare moment of public candor, as a genuine alarm. The models, the same models that had guided climate policy for 30 years, had not predicted this. They hadn't predicted it because they hadn't been built to predict it. Here's why that matters. Climate models are essentially very sophisticated guessing machines. They take the physics of the atmosphere, the ocean, the ice, and the land. They translate all of that into equations, and they run those equations forward through time to predict what happens next. These models are extraordinary achievements of science. They've been right about a great many things, but they have a blind spot. The blind spot is called marine ice sheet instability. It's a term scientists have known about for 50 years, but mostly treated as a distant theoretical concern, a worst-case scenario that might kick in someday under conditions far more extreme than what we'd see anytime soon. What the new data suggests is that we may already be inside that scenario.
To understand marine ice sheet instability, you need to understand what's unusual about West Antarctica. Most ice sheets sit on land that is above sea level. Greenland's ice, for example, rests on bedrock that sits above the ocean floor. If it melts, the water runs off. It's bad. But the process has natural breaks. West Antarctica is different. Most of its bedrock sits below sea level. The ice sheet is essentially sitting in a bowl beneath the ocean surface, held in place by its own mass pressing against underwater ridges along the coast. Those ridges act like corks in a bottle. Now imagine what happens when the cork starts to slip. Warm ocean water, water that has absorbed decades of excess heat from the atmosphere, is circulating under the ice shelf. It's not dramatic, it's not violent, it's just warm. A fraction of a degree warmer than it used to be. But it's persistent, and it's eating the underside of the ice from below. As the ice shelf thins, it loses its grip on those coastal ridges, and here is where the physics become terrifying. When a marine ice sheet begins to retreat past a ridge, gravity takes over. The ice doesn't just melt, it flows. The slope of the bedrock beneath West Antarctica tilts inward, deeper and deeper as you move toward the center. So as the ice retreats off the ridge, it encounters deeper water. Deeper water means more contact with warm ocean. More contact means faster melting. Faster melting means more retreat. More retreat means deeper water. It's a feedback loop, and once it starts, the current physics suggest it may not have an off switch. This is not a new theory. A scientist named John Mercer proposed it in 1978. He was largely ignored. For decades, the conventional wisdom held that even if this instability were real, it would take centuries to become relevant. Then, in 2024, a team of researchers published findings from a part of Antarctica called Thwaites Glacier. Thwaites is sometimes called the Doomsday Glacier. Scientists don't love that name. It sounds like a movie title, not a scientific designation. But the reason it exists is this. Thwaites is the size of Florida. If it collapses entirely into the ocean, sea levels around the world rise by 2 feet. Not eventually, not as part of a 1,000-year process. On a geological timescale, that would be almost instantaneous. What the 2024 data showed was that the warm water intrusion beneath Thwaites had extended further than any model projected. The grounding line, the place where the glacier meets the sea floor, had retreated by several kilometers more than expected, and the rate of retreat was accelerating. The models had been wrong. Not slightly wrong, significantly wrong. Here's where the ice cores come back in. The researchers drilling into the ancient ice weren't just looking for climate data. They were looking for something specific. Evidence of what happened the last time the Earth was as warm as it's about to become. That period is called the last interglacial, a warm interval that peaked roughly 125,000 years ago. During that time, global temperatures were about 1 to 1.5 degrees Celsius warmer than pre-industrial levels. Sound familiar? That's almost exactly the temperature range we're now entering. And during the last interglacial, sea levels were between 6 and 9 meters higher than they are today. 6 to 9 meters. That's between 20 and 30 feet. Now, some of that came from Greenland, and some came from thermal expansion of warming ocean water. But the math doesn't quite add up without a significant contribution from the West Antarctic ice sheet, which means it collapsed before, under conditions we are now recreating. The ice cores confirmed the timing. They showed chemical signatures of rapid warming, rapid ice loss, and rapid sea level change happening together in a way that previous models had assumed would take much longer to trigger. The ice remembered what happened last time. It was telling us what comes next. This is where the science stops being abstract. A 1-meter rise in sea level, which is now considered a realistic scenario for this century, not the distant future, puts parts of Miami, New Orleans, Jakarta, Amsterdam, Shanghai, Mumbai, and dozens of other coastal cities under regular flooding. Not underwater, not permanently submerged, at least not yet. But at 1 meter of rise, a storm surge that used to happen once every 100 years starts happening once every decade. Infrastructure built to survive a 100-year flood is hit by a 10-year flood. Insurance models collapse. Mortgages become uncollectible. Property values crater. Not because the land floods today, but because the market understands it will flood. The financial system, in other words, starts pricing in a future that the political system hasn't acknowledged yet. Now scale that to 2 meters, a scenario that, based on the new Antarctic data, some researchers now consider possible within this century if warming continues on its current trajectory. At 2 meters, we are no longer talking about flooding. We are talking about abandonment. Some of the most densely populated coastlines on Earth would need to be surrendered. Not in theory, not in some distant future, within the lifetime of children alive right now. And this is the part that the scientists who work on this topic find hardest to communicate. The decisions that determine whether we hit 2 meters, or 1 meter, or something closer to half a meter, are not decisions that will be made in Antarctica. They are decisions being made in parliaments and boardrooms and at gas stations right now.
Here is what we know. The ice is moving faster than expected. Here is what we don't know. Exactly how fast. The range of projections for sea level rise by 2100 has actually widened in recent years, not narrowed. That is a strange thing. Science usually gets more precise over time, but with West Antarctica, the new data has introduced uncertainties that didn't exist before. The lower end of projections, half a meter of rise by 2100, is still considered possible if emissions are cut dramatically in the next decade. The upper end, 2 meters or more, is now considered possible even with moderate emissions cuts, depending on how quickly the marine ice sheet instability develops. The uncertainty is not comforting, but it is honest. There is one other thing the new data revealed that doesn't fit neatly into the story of collapse. And this is important because science is rarely a single, clean narrative. Within the ice cores, researchers found something unexpected in the record of the last interglacial, evidence that the warming was not linear. There were periods of rapid acceleration, followed by periods of relative stability, followed by acceleration again. The ice sheet didn't collapse all at once. It pulsed. If that pattern repeats, it means we may have more time at certain stages than a simple linear projection suggests. It also means the eventual outcome, barring dramatic intervention, may still be the same. The pulses don't change the destination, they change the schedule.
The scientists who work on this don't describe their work the way you might expect. They are not, mostly, a panicked group. They are methodical. They are careful. They spend years getting one number right. They argue intensely with each other about hundredths of a degree and millimeters of sea level. But in private conversations, in papers with careful language about elevated risk and concerning trends, there is something that reads as urgency. One researcher who has spent decades measuring the grounding line of Antarctic glaciers described the experience this way. You develop an intimate relationship with these places. You know them in a way almost no one else does. And when you watch the numbers change, it doesn't feel like data. It feels like watching something you love get sick. That is not a scientific observation, but it is a human one. And perhaps that's the gap that matters most right now, between what the data shows and what the rest of us understand. The ice cores have spoken. The satellite measurements have confirmed it. The models have been revised. The information exists. Whether it reaches the decisions that matter is a different question entirely.